We're going to be discussing weak bonds in this lesson. We talked a little bit about it when we were discussing the development of dipoles, but we're going to explain it in a little bit more detail. And what we'll do is we'll use an example of a material or an element like argon, where argon, as we described using the Bohr model that we developed earlier on, the electrons are distributed around the positive charge of the nucleus. Now, with that large number of electrons associated with that argon atom, that isolated atom, if we bring into proximity another argon atom, what we can do is, over a period of time, a statistical reorganization of the electrons can occur, and ultimately what can develop is a dipole that occurs randomly throughout the structure, and occasionally it'll be plus on one side and minus on the other. So what can then happen as a result of the electron redistribution, we'll see that we can begin to develop some secondary bonds. So even though we think of argon as not being reactive, it can be, and it can develop some weak interactions that are attributed to these secondary bonds. But you need to recognize that the bond attraction associated with these secondary bonds is very weak, and any thermal energy tends to destroy those bonds. So these are temporary, and sometimes people refer to these as temporary dipoles or weak secondary bonds. Now again, I want to return to the picture of carbon in the chain associated with a polymer. Again, one of the things that I want to point out is that we have an interaxial angle of 109.5 degrees that is associated with the equal distribution of the carbons around that central carbon atom. And that's different than the hydrogen-oxygen-hydrogen bond of 104.5 degrees, and that is attributed to the presence of the dipoles that result when the charges become redistributed. So here are some examples of materials in which we have replaced the oxygen and we now have sulfur and nitrogen. And one of the things that you can begin to see is, as you begin to add increasingly more electronegative elements, the charge distribution is going to be much greater, and we're going to have the tendency to have more secondary bonding in the formation of the structure. Now, if we look in the first two cases, we see hydrogen, oxygen, and hydrogen, and in the next we see hydrogen, sulfur, and oxygen. And there are a lot of similarities in the compounds that form with oxygen and sulfur. But when we look over here at ammonia in terms of the valences that are associated, we have this pyramidal structure of nitrogen with 3 hydrogens. But again, what happens here is because of the distribution and the development of the dipole, we have these weak bonds. Now, what I would like to do is to extend this to a polymeric system. Now, the simple polymer that I want to use is the building block that's associated with polyethylene. And so we start out with the structure that we have on the left, and that's the basic building block. The double bond is broken, it's replaced with a single bond, and then that represents what we refer to as the polyethylene mer. And those polyethylene mers get put together, and we ultimately form a nice long chain. One of the things that we can do during processing is to extrude these materials, and basically when we think about extrusion, it's like squeezing a toothpaste and watching the toothpaste come out of the orifice of the toothpaste tube, or the dye in the case of an extrusion. And because of the flow lines that are associated with the process of extrusion, these polymer chains can line up one on top of the other. And when that particular situation occurs, what we can do is we can produce a structure that we refer to as high-density polyethylene. If we increase the temperature and those individual polymer chains are allowed to coil, then we can begin to reduce the density of the polyethylene. Now, if we look at weak bonds in that same material, and this time what we're going to do is we're going to periodically replace hydrogen with chlorine, and remember that chlorine is an electronegative element, and when we start replacing with chlorine that one polymer chain, and we do the same with another polymer chain, then what can happen is these two chains can come together and we can develop a hydrogen bond between the chlorine and the hydrogen, the chlorine and the hydrogen. So now what we've done is to develop a weak hydrogen bond between those chains. And that linear behavior that's associated with the weak hydrogen bond will persist longer than in the case of having only hydrogens there. And so we can maintain that higher density structure for slightly higher temperatures. However, as the temperature does go up, the hydrogen bonding will begin to dissipate, and as a result, this polymer structure will also begin to coil. In the next lesson, we're going to be developing some basic ideas in thermodynamics. Thank you.